All right, so do you remember we mentioned before that there was an old equation that we used for gravitational potential energy, and that was UG equals mgh. UG equals mgh. But when is it that you're able to use that formula?
When you're on the surface of the Earth, or like
Yeah,
near
when
the surface.
when you're close to the surface. So we talked about this last time, like when you're on the top of a slide or on top of a building, you're still relatively close to the surface of the Earth. But as soon as you're far away from the surface of the Earth, or maybe you're like on the surface of a different planet, you can't use this formula anymore. So instead, we're using a different formula, which is this one. UG equals negative G M1 M2 over R. Okay, so that's the other formula that we're using. Now, in a question, if you're using conservation of energy, you can't mix and match between these two equations. So if we look at question 1, it says a rocket is launched straight up from the Earth's surface. So initially, the rocket is near the surface of the Earth. And then it says, what is its speed when it's very far away? So at the final point, it's far away from the surface. We can't use UG equals mgh initially, and then UG equals negative gm1 m2 over r at the final state. We have to choose one equation for the whole problem. Does that make sense? We're okay with that? Yeah? Okay, so awesome. So in this case, because there's a point in the story where we're not close to the surface of the Earth, we need to use that second, more complicated equation for UG. Okay, we can't use mgh at all, even though we are close to the surface of the Earth at one point, we're not close to it at a different point in the story, so we have to use the harder equation. So when we do these problems, it's just like saying, you know, a ball is at the bottom of a ramp, and how high up the ramp will it roll before it comes to a stop, or what is its speed when it gets to a certain height. Okay, so we're using conservation of energy. So we're going to say E total initial. It's really the same like procedure as we've done before. The only difference is the formula for UG equals E total final. And in the last lecture, we talked a little bit about UG and when is UG 0. So if we're using the first equation over here, when would UG be 0? When is it that we would be able to just cross off? Yeah, good. So when the height, in general, it would be when the height is 0. If the height is 0, then UG is 0 if we're using equation 1. But if we're using equation 2, because at some point in the story, the object is not close to the surface of the Earth, when is UG 0 in this case?
R is 0.
Pardon, can you say when R is 0, did you say?
Yes.
If R is 0, when you divide by 0, do you get 0?
Isn't it when R is a really large number?
Yeah, good. If R approaches infinity, if R is very big, that's when UG will be 0, because a number divided by a huge number approaches 0. Okay, so if you're using equation 1, UG is 0 when the height is 0. But if you're using equation 2, UG is 0 when the R, or the distance from the center of the Earth or whatever other object you are near, when that R value is 0, infinity, when it's very, very large. Okay, so because in this problem, there's a point in the story where the rocket is not near the surface of the Earth, we have to use the equation UG equals negative gm1m2 over r for gravitational potential energy. So I'm going to put in the two types of energy here, EK initial plus UG initial. I'm not even going to put elastic at all. There's no spring in the question at all, so I can leave that out. EK final plus UG final. And let's start putting in equations. So I have EK is 1/2 mv initial squared. UG is minus, so don't forget that there's a minus sign here. So let me tell you one thing before we proceed. I just noticed one person joined the class from an external email account, so you're not using your .NET account. So in the future, please use your .NET account to get in, because that way nobody has to let you in. But a bigger reason, like a better reason for using that, is because I've been hearing stories that there are like trollers who have been entering people's Google Meet sessions and like posting inappropriate things or playing music or things that are like really inappropriate in the background and disturbing the class. So I'd like to like not allow people to get into the room if they're not coming in through their .NET account, just to avoid that from happening. If that ever did happen, we're going to have to all leave this room, and I'll go into Blackboard and change the link, and then we'll go into the new room. Okay, but hopefully that doesn't happen to us in this last banhammer. Is that what that's called, Alex? Banhammer? Um, so hopefully that doesn't happen, but to avoid that, the best way is to not allow people in who are not in this room, like part of our class. So if you can all just join using your .NET account, then we don't need to even let anybody in. Okay, so for the UGI, a very common mistake is that people forget to put in the negative. So make sure you're putting the negative sign in. Negative G, M1, M2 over R equals, and this is initial, equals EK final, which is 1/2 MV final squared, and then plus UG final, again, is a negative G M1, M2 over R final. Okay, so out of all of these, is there anything we can cross off because something is 0? As the leader of the call, I have the permission to kick people out. Yeah, I do. Sometimes it's like a little bit hard to know who the intruder is, but yeah, you're right. I mean, I can see everybody's name in the class, so I know all of you. And if there's somebody I don't recognize, I can kick people out. Sometimes people have joined with like the name of the instructor or a person. I don't know how they're doing it, but it's, yeah. Okay, so UG final is 0. So thanks, Yuchin. So that makes sense. It says UG final is 0, and that's because this RF over here in the question, it says that you're very far away from the Earth. What is the speed when it is very far away from the Earth? And so this R final is approaching infinity. And when something approaches infinity in the denominator, the whole thing approaches 0. So that UG final is actually 0 here. And thanks for answering the question about using MGH. So that was a good question, and that's a common mistake. And thanks for answering that. So if you are at any point the object is not close to the surface of the Earth, then you have to use that negative GM1, M2 over R equation for both sides of the formula. Even though you're close to the surface of the Earth initially, you can't use MGH. You have to use the same formula on both sides. Okay. All right, so because it says what is its speed, so we're looking for the final velocity when it is very far away. So we're looking for this final velocity. Very far away implies that the final r, which is the distance from the center of the Earth, is infinity. Okay, so when you see the words very far away, okay, then that means that the distance is infinity. Okay, because I'm not giving you any actual value. I'm not saying how far away, so you have to assume it's infinitely far away. Do we just assume RF goes to 0? So RF is not 0, RF is infinity, because it says infinitely far, like because it's very far away, we're going to assume that means infinitely far away. If RF goes to infinity, then that whole term goes to 0. Okay, because when you divide by a really huge number, you get a really tiny number, so it's approaching 0. You're welcome. Okay, so we're solving for V final. So now if we look at the equation, this mass initially, when you see this mass over here, which mass is it that we're referring to? We have two objects really here. We have the rocket and we have the Earth. So what is that the mass of? The mass of the rocket, perfect. So I'm going to put a little r here. And for the second formula, where I have G m1 m2 over r, what is that? What are those two the masses of? What's m1 and m2? The mass of?
Mass of the Earth and the mass of the rocket.
Yeah, good. So it doesn't matter what order you put it in. One's the mass of the rocket, the other one's the mass of the Earth. And then on the right side of the equation, 1/2 mv squared, what's that mass of?
Mass of the rocket.
Yeah, good. Because it's the rocket that's moving. It's the rocket that has the kinetic energy. Okay, awesome. Okay.
So I can cancel all the mass of the rocket out.
Yeah, so the mass of the rocket is not even given to you, which is fine because it can all cancel out. Mass of the rocket, mass of the rocket. Perfect. Okay, so we know the initial velocity of the rocket. What are we going to enter for initial velocity of the rocket?
15 kilometers per second, but we will change it to meters.
Right, good. So 15,000.
Time.
Yeah, good. And then the mass of the Earth, we're going to have to get that from a different page. It's on the formula sheet. What are we going to put for the initial radius, the r initial?
The radius of the Earth.
Yeah, because the object is on the surface, the rocket is on the surface of the Earth. So the distance between the center of the rocket and the center of the Earth, we're going to assume is just the radius of the Earth because the rocket's volume is very small in comparison to the radius of the Earth. Okay. And that's it really. So as long as we know those values for the mass of the Earth and the radius of the Earth, then we're okay. So I'm going to go back and find those values. Does anybody know them? I'll show you where they are. Okay, so it says it right here. I'll put it on this page as well. It'll be on the formula sheet too. Okay. So the mass of the Earth.
5.97 times
Yeah.
10
Thank
power
you.
of 24.
Good. So the mass of the Earth and the radius of the Earth are I just put them in here. Okay. All right, so then you can just plug everything in. You know the initial velocity, you just need to make sure it's in meters per second, and you're solving for that V final. So I'll let you go ahead and do that and make sure that you're getting the right answer. Now note, the answer, like if you were to just plug in all your numbers, your answer would be in meters per second, and you're welcome to use any prefixes, like you should end up getting 9990 meters per second. And if you don't want the number to be so big, you can always use a prefix like kilo to make the number smaller, especially if you have several zeros at the end and you don't want to have to enter those zeros into your online quizzes. You can always use a prefix, so kilo or mega, or if it's in the other direction, you can use things like mila, like with a little m, or micro would just be a u, or nano for times 10 to the -9 is a little n. Okay, so you're welcome to use prefixes, or you can just put in all the zeros, either trailing or leading zeros, trailing at the end or leading before the digit. Okay, so I'll give you some time to just plug everything in and let me know if you're getting the right answer. You can just say got it if you got the right answer. And I didn't write it down, but the value of G is 6.67 times 10 to the -11. Okay, awesome. So a couple people are getting it. I see. Okay. All right, so if you just plug everything in, you can leave your answer in meters per second. You're welcome to change it to kilometers per second if you want to, but you don't have to. Awesome. Okay, question 2. A meteoroid heading straight from Earth for Earth has a speed, awesome, has a speed of 14.7 kilometers per second relative to the center of Earth as it crosses our moon's orbit, a distance of 3.84 times 10 to the 8 meters from the Earth's center. Okay, so this is a distance already from the center of the Earth, so you don't need to add the radius of the Earth to it. What is the meteoroid's speed as it hits the Earth? You can neglect the effects of the moon, Earth's atmosphere, and any motion of the Earth. Okay, so we're going to do the same thing. We're going to set up the E total initial equals E total final. And we're going to cross off whichever types of energy we don't have, either initially or final. So I'll just put them in. Again, I'm not even bothering with elastic potential energy because there's no spring in the question at all. Okay, so initially, the meteoroid has a speed of 14.8 kilometers per second. So there is kinetic energy initially. Initially, the object, the meteoroid, has a distance of 3.84 times 10 to the 8 meters from the Earth's center. That's not an infinite distance, so it does have gravitational potential energy initially. At the end, it says, what is the meteoroid's speed as it hits the Earth? So it's asking for the speed, so it must have kinetic energy, final, because it's looking for the speed, and as it hits the Earth. So does it have gravitational potential energy, final? Okay, so somebody said no. Any other? Does anybody else think differently? Okay, so if you're using the equation UG equals MGH, then Sarth would be correct because final, the height we would say is 0, so UG is 0. But are we using that equation? Nope. So the reason why we're not using that equation is because at one point in the story, the meteoroid was not close to the surface of the Earth. So we have to use that long equation for UG, which means we have to use it all the time. So we're not using this equation at all in this problem. We're using this equation, UG equals negative G M1 M2 over R. Okay, so in this case, when we're using this formula, when is it that the UG would be 0? What is the value of R that makes UG 0?
Infinity.
Yeah, good. So if R is infinity, so if the question says you're very far away from the Earth, or it says you're infinitely far away or something, that's when UG would be 0. In this case, it wants to know what is the speed of the meteoroid when it hits the Earth. So the R is not infinity.
The radius of the Earth.
Yeah, the R is the radius of the Earth. So it's not going to be 0. So in this case, none of the terms get crossed off. If they both equal gravity, then why can't we interchange them if we know their respective variables? Oh, that's a great question. So I think you're referring to the two equations, like UG equals MGH and UG equals negative GM1 M2 over R. Is that correct, Michael? Okay, so the reason why we can't interchange them is because they both have a different reference position. For UG equals MGH, the reference position is a height of 0. For UG equals negative GM1 M2 over R, the reference position is R equals infinity. You can't interchange them because what matters in this formula when you're using the conservation of energy is not what the value of UG is, it's what the difference in UG is. So what the change is. So when you do UG final minus UG initial, whether you're using the first equation or the second equation, you'll get the same value. But when you find UG initial with one equation, like say MGH, or UG initial with the other equation, you won't get the same value. So you need to choose one equation or the other for the entire problem. You're not getting the same value, but if you use the same equation, the difference in UG, so the change in UG final minus UG initial, would be the same either way. So if you're talking about a boy sliding down a slide, the final UG minus the initial UG for the boy would be equal whether you're using MGH or the negative GM1M2 over our equation. But the value of UG initial for the boy with MGH equation or UG equals negative GM1M2 over our equation, you would get two different UG values using those two different equations. Whoever's mic is on, if you can just turn it off because we can hear a lot of noise. Okay, so the UG values will be different from each other, but the change in UG would be the same as long as you're allowed to use that equation, i.e. if in both cases, initial and final, you're near the surface of the Earth both times. Does that make sense, Michael? And everybody else?
Yeah.
Okay, so Alex,
Thank
what if
you.
we set, no problem, what if we set h to be the radius of the Earth? Then G would change. Yeah, exactly. You can't use the 9.8 for G. Yeah, the G is a different value when you're far away from the surface of the Earth, the little g, 9.80. So you can't use that equation. So you have to look at the problem, and the first thing you ask yourself is, are you close to the surface of the Earth for the entire problem? If it's yes, like the boy sliding down the slide, use the MGH equation. If you use the negative GM1M2 over our equation, you'll still get the question right. It's just longer. It's more work because now you have to put in the mass of the Earth and the radius of the Earth. But if the answer to your question is no, if at any point in the story you're not close to the surface of the Earth, you have to use the longer equation for both initial and final. Okay? So let's start putting in our equations. So EK initial is 1/2 mv initial squared. What is this the mass of? This m here that I just wrote, is that the mass of the meteoroid or the mass of Earth?
Meteoroid.
Yeah, good, because it's the object that has the speed. And then UG initial is minus G, mass of the meteoroid, mass of the Earth, over the R initial equals EK final, so 1/2 mass, we're talking about the meteoroid who has the kinetic energy because it's the one that's moving, V final squared, minus, remember, don't forget that minus, UG has a minus sign now, G, mass of the meteoroid, mass of the Earth, over our final. And we're looking for what is the meteoroid's speed as it hits the Earth. So we're looking for the V final over here. So let's just make sure we know what everything is. So V initial is the initial velocity of the meteoroid. We just need to change it to meters per second rather than kilometers per second. What about R initial? What's the R initial going to be? Yeah, the radius of the Earth. So initially, is the meteoroid at the surface of the Earth? What should the initial R be? Initially, the meteoroid,
3.84
yeah,
times 10 over 8.
good. Initially, it tells us that the meteoroid is 3.84 times 10 to the 8 meters from the Earth's center. So that is the R initial. Okay, so this is our R initial over here. It's already in meters, so we don't have to change it. What is the meteoroid's speed as it hits the Earth? So then what's the R final going to be? Now it's hit
The
the Earth.
radius of the Earth.
Yeah, good. So the R final is the radius of the Earth here, because now the meteoroid is on the surface of the Earth. Okay, so now you can start to plug everything in. You can use the values for the radius and the mass of the Earth that are up here from the first question, and rearrange and solve for V final, and then plug everything in. Let me know if you're getting this answer. You can just type got it. Awesome. Awesome. Okay, so this is what you're going to see a lot on your quiz, and you'll see questions like this on your exam. So there's no tests. You are like this content is not on any tests anymore. Test 5, for those of you who haven't written it, is on the 4 lectures before. Let me look. So it's on lectures 18, 19, sorry, 17, 18, 19, and 20. So it's not on lectures 21 or 22. The final exam is cumulative, so it's going to have questions right from the beginning, like adding vectors and even maybe a tiny bit of SOHCAHTOA, but most of it will be like 1D kinematics, a bit of 2D kinematics, forces, momentum, collisions, things like that. Okay, it's going to include everything. Okay, so are we ready to move on to the next question? Okay. Okay, so the next topic is escape speed. It's very similar to what we've already been doing. It's just a new concept here. So when you launch an object from the surface of a planet with not enough speed, so let's say you take a ball right now and you throw it up into the air, what's going to happen to that ball eventually? Is it going to keep going up forever? Depends on how hard you throw it. But let's say you throw it yourself. What's going to happen to the ball? It'll come back down, exactly. If you throw it faster, it'll still come back down. If you throw it faster, it'll still come back down. But at some speed, if you had some rocket and it got shot up with a fast enough, like a high enough speed, it would eventually keep going and never come to a stop. It will never come back down, right? What's William saying? Depends on how hard it's thrown. Yeah. Okay, so when an object is launched from the surface of a planet with insufficient speed, so like any speed we're able to give it, it will eventually come to a stop and then gravity will pull it back down. The only way an object can escape from the gravitational pull of the planet is for it to never stop. Thus, the object must continue moving away from the planet forever. The minimum launch speed for it to escape, which is called the escape speed, will cause the object to stop only when it reaches a final distance of infinity. Okay, so that last line is really important. It will stop, so the V final is 0, and the final distance, so that would be the R final, is infinity. Okay, so the V initial is the escape speed if the V final is 0 and the R final is infinity. So that's the key here. We're going to do the exact same thing as we've always been doing with the conservation of energy. But the question is asking, what is the minimum speed needed to escape from the surface of the asteroid or from the surface of any planet? Then what's important to know is that that implies that the object's final velocity is 0 and its final radius, or the final distance from the center of the planet, is infinity. Okay, so let's look at this question. A certain spherical asteroid has a mass of 3.5 times 10 to 16 kilograms and a radius of 8.8 kilometers. What is the minimum speed needed to escape from the surface of this asteroid? Okay, so we're going to do E total initial equals E total final, like always. And then we'll include those two types of energy, E kinetic energy initial and UG initial equals E kinetic final plus UG final. Now, which equation do we have to use for UG? The easy one or the hard one?
The hard one.
Yeah, good. So I'm going to put in my equations. 1/2 mv initial squared plus, instead of plus, I'm going to change that to a minus because the equation is negative. G m1 m2 over r equals 1/2 mv final squared. This is our initial minus G m1 m2 over r final. First, let's figure out what these m's are. So initially, when we're looking at kinetic energy initial, that 1/2 mv squared, what is that m referring to? The mass of what? It's kind of tricky because it wasn't mentioned.
Spherical, certain spherical.
So this is a spherical asteroid. So you're talking about an asteroid, and the question is, what's the minimum speed needed to escape from the surface of the asteroid? So the object we're talking about is whatever the object is that's trying to escape. It's not mentioned in the question because it doesn't matter. Remember, every time we've done this, we've been canceling out the mass of the object. So this is saying, what is the minimum speed that the object, any object, whether it's a rocket or a person or a ball, what is the minimum speed that that object needs to escape from the surface of the asteroid? So we're talking about the object. So this mass is the mass of the object. I'll just put an O for object. And so then we have the mass of an object. And what's the other mass? Yeah, exactly. The mass of the object that is escaping, Keithan. Perfect. So the mass of the other object, so we have the mass of the object and the mass of, for G m1, m2, what's that m2 going to be? The asteroid, perfect. So I'll just put an A here for asteroid. So we have two objects here, some random object that we don't know what it is, and the asteroid. So those are the two masses. And then there's our initial. What is the R initial referring to? Because initially, the object is on the asteroid.
8.8 kilometers.
Yeah, good. It's the radius of the asteroid. So I'm just going to call this the radius of the asteroid here. Okay, equals 1/2 mv squared. We're still talking about the object here, so this is mass of the object. And then finally, we still have the mass of the object, mass of the asteroid. Now, what about the final R?
Infinity.
Yeah, good, because we want the object to escape the asteroid. And so for it to escape, it must reach a final velocity of 0 when it has reached like a distance away of infinity. So this over here is infinity. Okay, so now what is that V final going to be?
0.
Good. So anytime you have a question that asks for the escape speed or the minimum speed needed to escape from the surface of a planet or an asteroid or something, the V final is 0 and the R final is infinity, which means that the UG final is 0. So for all of these questions, EK final is 0 and UG final is 0. Okay, so now that makes the question a little bit easier. You're trying to solve for what variable here? What is the minimum speed needed to escape?
V initial.
Yeah, you're looking for V initial. What can you do with these mass of the objects here?
Both mass cancel out.
Yeah, good. Okay, you could have canceled them out of everything, but those other ones are 0 anyways now. And then you can rearrange and solve for velocity initial. Okay, so I'm going to let you do that. You know all the information now. You're just rearranging for V initial and then plugging everything in. So the formula for escape speed is basically, well, not quite. You have your 1/2 V initial squared minus G m of the asteroid or whatever the planet is over the radius of the asteroid or whatever the planet is. And on the right side, you just have 0 because everything cancels out and it's giving you 0. Okay. And then I'm just going to make some more space here. And then you're solving for V initial. So you're going to bring the G MA over RA to the other side. And then you're going to get rid of the 1/2. So you can times both sides by 2. And then you're going to square root 2g mass of whatever this is, asteroid in this case, but it could have been a different planet. Like it could be a planet, mass of the Earth, radius of the Earth, or maybe you're on the moon, it would be mass of the moon, radius of the moon. So V initial, which is the escape velocity, and I can call this escape. This is always the formula for the escape velocity. You're not going to get this formula though. So you're either going to memorize it or you're just going to realize that the final kinetic energy and the final gravitational potential energy is 0, and then you can rearrange and solve for it. Okay, so people are getting it. That's awesome. I'm going to just plug in the numbers. The mass of the asteroid was given. And the radius of the asteroid is 8.8 kilometers. Do you have to show the rearranging in the exam if you memorize the formula? Good question. No, you don't have to show the rearranging of the formula. If you like to just memorize this equation, it's fine. But if any of it is wrong, you won't be getting any part marks for your work that you've done previously to that because you didn't show any of it. Okay, so you're welcome to memorize it. Make sure you memorize it correctly because otherwise you'll be losing a lot of marks for that question because you won't really have any work to show. No problem. Okay. Any other questions there? Okay, let's move on to number 4. So number 4 says, what's the ratio of the minimum escape speed of a rocket launched from sea level to the minimum escape speed of a rocket that's launched from Mount Everest, which has an altitude of 8.85 kilometers? So we're trying to find the escape speed for a rocket at sea level, implying from Earth, sea level of Earth, to the escape speed of a rocket that's launched on top of Mount Everest, so on this with this new altitude. And then they want the ratio. So what does that mean when they ask for the ratio? What do they want you to do with those two values? What does ratio mean? Divide them. Perfect. Okay. So what they're asking for is, what is the escape? I'm going to write it like this. Escape velocity launched from sea level divided by the escape velocity launched from Mount Everest. So when they ask for the ratio of one thing to another, then that just means the first thing divided by the other. So the escape velocity of one, and then to reduce it if possible. Exactly. So you actually divide them and get the number. So you're going to divide on your calculator and get a decimal. So you're not even really necessarily reducing. You can just divide and get a decimal. Okay, so I'm going to use the formula we derived from above, which was the escape velocity is 2gm over r over the same thing on the bottom. Okay, so what is the m that we're referring to here? It's not the mass of the asteroid anymore.
Mass of Earth.
Yeah, good. So in both cases, it's the mass of the Earth. And then g is a constant, so we don't need to worry about that. And then what about r? So when we're at sea level, what is the r referring to?
Radius of the Earth.
Radius of the Earth.
Perfect. Awesome. So now what about when we're at Mount Everest, when we're on the top of Mount Everest? What's the r referring to?
Radius of the Earth plus the altitude of Mount Everest.
Excellent. Makes sense, because that's the new r value, the distance from the center of whatever the object is that's trying to escape to the center of the Earth. Okay, so now all we're doing is trying to simplify all this. We can plug in all the numbers and get the number on top and divide it by the number on the bottom. But perhaps I'm on a different planet. Like, let's say in a question on the exam, I tell you you're on a different planet and I don't give you some of the information like the mass of the planet. Well, it would be okay because it would cancel out. So let's try to simplify this. First of all, this square root. When you have a fraction with a square root on top and bottom, you can rewrite it with like one big square root instead. The next thing, when you're dividing one fraction by another fraction, how can you simplify that? A fraction divided by another fraction is like the first fraction times by the second fraction. What do you have to do to it?
The denominator on the numerator and numerator.
Yeah, good. So you flip the second fraction and you multiply instead of divide. And there's still a big square root everywhere. Okay, so just on the side, if I had something like 1/2 divided by 3/4, that would be the same as saying 1/2 times 4/3. That's all that I'm doing here. Okay, so I'm flipping the denominator. Okay. So now what can cancel out?
2g mass of Earth.
Yeah, good. Good. And that's it. So now my RE plus 8850 over RE. That's all I really have to plug in now. So it makes it a little bit easier. Equals the square root of the radius of the Earth. Was that 6.37 times 10 to the 3 kilometers, I think? So times 10 to the 6. Let me check. My brain doesn't work anymore. Yeah, 6.37 times 10 to the 6 meters. Plus 8850 over the radius of the Earth, 6.37 times 10 to the 6. And then when I divide those, I should get 1.0007. So the ratio is 1.0007. So basically at sea level, it's harder. It's a tiny bit harder, or you need higher velocity to escape from sea level than you would if you were at the top of Mount Everest. Because when you're at sea level, the force of gravity acting on you is bigger. So it's harder to escape the gravitational pull of the Earth. Okay, any questions there? All right, let's move on. Let me see how many questions there are. Yeah, this is the last one. Okay, so they're all fairly repetitive. Just remember that whole escape velocity thing means that the final kinetic energy and the final gravitational potential energy is 0, and then you solve the problem the same way. Okay, number 5, you've been visiting a distant planet. Your measurements have determined that the planet's mass is twice that of the Earth, but the free fall acceleration at the surface is only a quarter the amount. The mass of the Earth is given. What is the planet's radius? Okay, the planet's mass is twice that of the Earth. The free fall acceleration at the surface is a quarter. What does that mean, the free fall acceleration? What variable is that?
Gravity?
Yeah, good. So little g, perfect. So little g, they're saying, is 1/4 the amount of the g that's on Earth. So do you remember from the last lecture what the formula is for little g? I'll
It's
drive it.
g. Little g is equal to big G times mass of planet divided by r squared.
Yeah.
Oh, that. Oh,
Yeah, you're right. So I'm just going to write the FG equation first. So
okay.
this is m1, m2 over r squared, where one of these mass, let's say one of them is the mass of the object, the other one is the mass of the Earth, if we're on Earth. Okay, so now if we're looking for if we use the other equation for FG, FG equals mg. If we set those two equations equal to each other, we get g, mass of the object, mass of the Earth, over r of the Earth squared, this is mass of the object here, equals mass of the object times g. Cancel out my mass of my object, so my g is the rest of the equation that doesn't have mass of the object. So it would be g, mass of the Earth, over radius of the Earth squared. That's the formula to calculate little g. Okay, so it's telling me that the little g is a quarter of the size of the little g on Earth. So it's a quarter the size. And it's telling me that the mass is twice the size. So the mass of this other distant planet is twice the size of the mass of Earth. So what does the radius have to be so that the little g ends up being a quarter of the size, remembering that the radius is squared? So what do we need the whole denominator to be? The denominator to be so that g is a quarter. We have 2 times as big on the numerator. What does the denominator need to be to make that whole thing be a quarter? 2 over what would be a quarter? 2 over 8, good. So we need the denominator to be 8 so that the numerator we know is 2 times as big. The denominator, if it was 8 times as big, then the whole thing, 2 over 8, is a quarter. Then the g would be a quarter the size. So what does the r have to be in the denominator in order for the whole denominator to be 8 times as big? Remembering that it's being squared. What number do you square to get 8? Good. Square root of 8. So the radius of this other planet has to be the square root of 8 times the radius of the Earth. So do people want to speak up and ask questions now? Because I know that was confusing. Or type your questions.
Do we have to do this way, or can we do it
No.
in a different way?
Yeah, so why don't you tell me which way you would do it?
I would have done it set 1 second. I did this all in my head. I have to write it down, then say it.
Okay, no problem. You could do it like this if you want. So you could say the g value on Earth is 9.8, and let's times it by a quarter, equals the g value the capital G is 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the 24, but we're on this other planet which has a mass that's twice as big, so it's twice as much. And now we're looking for the radius of this other planet. And
Yeah,
then you
that's
can
how I
solve
was
for it.
thinking about it.
Yeah, you can do that. The only thing is this 9.8 that we started off with was an estimate, right? Because that number is actually 9.813 something. So doing it like this is a little bit less accurate. The other thing you could have done is you could have found the G for Earth, because this could be like a different planet too. Like it didn't have to, when they compared it, they could say it's twice, the planet's mass is twice that of like the moon. And they weren't talking about the mass of the Earth at all. So this 9.8 wouldn't be relevant. You would have to find the number first. So what you could do is use that G equation first to find out what the G is on that planet or whatever it is. So this equation here, G equals G mass of the planet over radius of the planet squared. So let's say instead the question said the planet's mass is twice that of the moon, but the free fall acceleration at the surface is a fourth as large. And then I said the mass of the moon is given and its radius is given. You would first have to find the G of the moon, right? Sub that value in over here and say, okay, well now we know that the G is a quarter the size and we can solve for the new R. So you can do it with numbers, like calculating the numbers first if you want. Instead of the ratio way, like the way that I've been doing it is just like examining the values and making the left side of the equation equal to the right side. Does anybody want to ask questions here? Because I know that still is confusing.
Can I just like instead of 1/4 times 9.8, I can write 1/4 times GM over R squared, and then I cancel both masses, both G, and then I solve it for R squared.
Yeah, so we can do that here. So this is the original planet, like what they're comparing it to. So in this case, they're comparing it to the Earth. In my new example, it would have been to the moon. So it's kind of like this. So this is radius of the Earth squared. And so we know it's a quarter that amount. So this is the little g over here. That's the formula for little g. So they're saying this is the little g of the Earth. So we're saying it's a quarter of the little g of Earth. And what is the new r going to be? So you can do it like that. You know all the values on the left side, and you know everything on the right except for the little r. So it should end up being root 8 times the radius of the Earth when you're done. But you don't have to do it the way I originally did it with the red ink. Okay, so Alex, so your question is, where did you get the root 8 from? So this is just one way that you can do the question if you like. You can look at what's happening to your variables on the left of the equal and on the right of the equal sign. So on the left of the equal sign, the question says that the G is a quarter the amount. So that's why I put times a quarter. On the right side of the equation, the question says that the mass is twice as much. So then we had to say, okay, well, what do I need to do to my R so that both sides of the equation are the same? The left side needs to be a quarter. The right side needs to match up and be a quarter. So we have 2 on the top. So the bottom needs to be times by 8. So that would get 2 over 8, which is a quarter. But it's in a root, like it's being squared. So we have to times it by root 8. So that when we square that, we get 8. So then we'd have 2 over 8 on the right side, which matches with the 1 over 4 on the left side. So Alex, let me know if that answers your question. And I realize that's not the way a lot of people want to do this problem, and that's totally fine. So instead, we wrote G, the formula for G, times a quarter, because it says that it's a quarter the amount. And then on the right side of the equation, we put in all the numbers and we solved for the R. And when you solve for the R, you should find out that it's root 8 times the radius of the Earth. So that 1.8 times 10 to the 7 meters should be the same as the radius of the Earth times by root 8. Okay, William, I sort of substituted values and got square root 8 radius of the Earth squared, which ends up being the same, yeah. 8 times the radius of the Earth squared, and then when you square root all of that, you get root 8 times the radius of the Earth. Perfect, it's the same. So however you're approaching this, I'm totally fine with it as long as you're getting the answer. So is anybody stuck on getting the answer here? You can do it by plugging in numbers or just by looking at those fractions or whatever's being multiplied to make both sides equal each other. So let me know now if you want to go over this one again, part A. Okay. We'll leave that one alone. If you have any individual questions, feel free to, if you feel more comfortable going into the individual questions Google Meet link, go ahead and go there because Rohit should be there as well. And if you have any questions you want to ask everyone together here, feel free to do that as well. Okay, so we're going to move on to B. To get back to Earth, you need to escape the planet. What's the minimum speed that your rocket needs? So what are we looking for? What is that called, that variable? You're trying to escape a planet. We're looking for speed. Yeah, escape speed. So this was all part A. For part B, we're looking for V escape. Okay, so like was mentioned, if you want to, you can memorize the formula. But if you don't want to memorize the formula, I'm going to start from scratch. So I'm going to say E total initial equals E total final, which means E kinetic plus gravitational potential equals final kinetic and final gravitational potential. But when you're looking for the escape velocity, you finally reached an R value or a distance of infinity when you come to a stop. So you've come to a stop, so this is 0, and your R value is infinity, so this is 0 as well. So now we have 1/2 mv initial squared minus g m over r equals 0. So one of them is the object, and the other one is the planet, whatever the planet is. I'll call it P. And the mass of the objects can cancel out. And so now we're looking for V initial.
هنا تعالى الراجل اللي جاي.
And now we can solve for V initial, and there's a square root here, right? Okay. And that's it. So we can plug in all the values that we know. G 6.67 times 10 to the negative 11. The mass of the planet, we know it's twice the mass of Earth, so it's 5.97 times 10 to the 24 times 2 over the radius of the planet, which we solved in part 1, which was root 8 times the radius of the Earth. I'll just write it like that. Root 8 times the radius of the Earth. Okay, so the radius of the planet, we got 1.8 times 10 to the 7, which should be the same as root 8 times the radius of the Earth, but I'm going to write it out because people might get confused.